5, I think you use numbers something like that last time. If I ask you which one has a bigger relationship, well, it may be tempting to say this, but we don't know, because maybe it just has more variation in x and y. How to solve the problem? How to solve it? Well, if we take the average cross product and we divide by something. We divide by something, give me a hint, it's taking the square root of something. Taking the square root of what? Well, let's put this down and see if this makes sense to us. Times what have we done there?
Taking the square root of the square deviations of x and y.
Yep, we've divided by, well, the square root of something. Well, what is this? This is the variance for x, and the other one's the variance for y. So what have we done? Well, what's the square root of the variance? It's the standard deviation. So what are we dividing this average cross product by, this covariance by? The product of
The combined standard.
standard deviations, exactly. We are dividing it by the product of standard deviations. If you want, you can just rewrite this whole denominator. To simplify it, you can just write it as Sx, Sy. Standard deviation of x, standard deviation of y. Now why? Why? Why are we dividing it by this product of standard deviations? Kind of seems arbitrary when you first look at it.
Can you tell us more about what goes into a standard deviation?
Oh, I think you're really, really close. It's telling us what? Well, we have this problem, right? We have this problem of variation. Of saying, well, we got variation in x, variation in y, when really we want just that cross variation. So, what do you think this is representing here? This is a measure of variation, of variance in x, and this is a measure of variance in y. Don't worry about the fact that I'm taking the square root of it. I'm just getting it into original units. We know that because this is a variance. The two are variances, so I'm getting standard deviations there. So the logic of it is that when I take the covariance and divide by the product of the standard deviations, what am I doing? I'm getting rid of, I mean, that's a crude way of putting it, but we'll talk about it. I'm getting rid of what? X sub I minus the mean, and Y sub I minus the mean. Okay? Those two things that we didn't want, by dividing by the product of standard deviations, I'm getting rid of them. Now, what does it mean to get rid of them? That doesn't sound very good. What are we actually doing? We are doing something called standardizing. Standardizing. And what does standardizing mean? Standardizing means, in statistics, when we divide by standard deviation. Now I'm just putting deviation here. I'm going to put in brackets S, because here we have two standard deviations. But in other contexts where we only have one standard deviation, when we're doing things like z-scores later, we are going to standardize and there'll only be the one. The key, though, is when you're standardizing, you're dividing by standard deviations. Now why? Why does this work? And what does it do? What's the effect of this? Well, the effect is to, like I say, kind of get rid of this stuff. But why? many times in statistics and a lot of math, if you look at ratios, you can decode a lot of problems. Let me put it right here. Let's just put a ratio here, A over B. Let's talk about what this means. How do we interpret this? A over B. Well, if you think of B, okay, B as being, you can think of it as being somewhat of a base here. It's the base. Then you're looking at how much of A there is relative to B, right? How much of A there, and we all know that, how much of A there is relative to B. Some of you are thinking, geez, you're talking about stuff we learned in grade 10, but it's important. A over B, if I take 2 over 4, interpret it with that ratio. Well, of 4, there's 2. Now, this ratio, imagine if it could have a maximum of 1. Then what this is measuring is how much of A is there relative to a maximum number. Okay, a maximum number. So that when A and B are the same, this here is equal to 1.0. Well, look at this formula that we've developed. We'll give it a name in a second, but look at this covariance divided by this product. You can look at the big formula, it unpacks it for us, or you can look at it just here. What is this? What is actually going on when we divide by the product of standard deviations? And keep this in mind. Use this. This is going to help. First of all, let's take care of one thing. Why is it the product on the bottom?
That's the maximum.
Well, it's a maximum, right? We've got a maximum on the bottom. And we can establish why it's the product on the bottom, because what do we do in the numerator? We took products, right? So it makes sense that the denominator would also be a product. So we have here the product of standard deviations, and what is that denominator getting at? It's saying, look, you have variability in X. This is what it's saying, if it could speak. It's saying, you have variability in X, you have variability in Y. Let's multiply them to get the maximum covariation possible. Okay? The maximum covariation possible for this particular data is reflected by the product of the variances or standard deviations. That's what this number is down here, is the B. Here's what you have to play with. That's what it's telling you. This is the variation you have to play with. I'm going to make an arbitrary number for that. Instead of 4, I'm going to say, for one given data set, let's say it's equal to 10. What does the numerator do now? The numerator, because it's taking the sum of cross products and not the sum of variances, if it took the product of variances, it wouldn't be very exciting. It's taking the sum of the cross products, is telling you what? How much of this is being accounted for by what? How much of it is being accounted for by not variation in X, variation in Y, but by the cross variation, the cross product. So when we look at our covariance here, the covariance is a proportion of what this is. Because if you think here as that being the base, the B part in the ratio, that's giving you the kind of like the sandbox you're playing in. Here are the dimensions of the sandbox. Now how much are you going to fill it? Okay? Perfect analogy, actually. Okay? It just came to mind. I've had an insight. Okay. There's the sandbox. Okay. There's the sandbox. There's you. And there's somebody else. Okay. I'm talking about when you were younger. This wouldn't apply now. But there's you, and there's your friend, and you're going to go play in the sandbox. You want to see how well you get along. Well, maybe the example what I'm trying to say is that if you get along really well, you'll play all over the sandbox. Let's say it's an amusement park, okay? Not a sandbox, an amusement park. There's one ride, there's another ride, there's another ride, and there's another ride. Now, if you two get along, how many rides are you gonna play on together? All of them, okay? But if you don't get along very well, maybe you'll just play on one ride, then you'll say, okay, go your own way, we don't get along. So, once you enter the sandbox, we'll see if you tap into all of the rides. But before you enter the situation, what do we have to define? Not the sandbox, the amusement park. We have to define the limits on the amusement park. How big is the park? If you go to a small park, we have to define that. If you go to a big park, we have to define it. That's the same idea as what this is doing in the denominator. It's defining the space available to play in. If there's a really strong relationship between X and Y, then what does this do? Basically maximizes the space, right? Because then you look impressive, you say, out of all the space you guys have to play, and you played in all of it. Wow, you guys have a strong relationship. See? So what is this going to go to if you have a strong relationship? This whole thing, this whole ratio should go to what? Go to 1. Should go to 1. If you don't have a strong relationship, maybe you get into the amusement park, you pay your ticket, you go in, you look at each other, you go, I never want to see you again. You turn around, walk the other way, how much of a relationship do you have? 0. You have 0 because of all the games that you could play, of all the space you could share, you share none. Okay? Does this make sense? This is what we've just defined. The covariance divided by the product of standard deviations has a special name. Does anyone know what it's called? Correlation coefficient. It is the correlation coefficient. Coefficient R. Okay, now we have to narrow our definition a little bit, because if we just say it's a correlation coefficient, there are many different types of correlation coefficients. Okay? So we're going to call it the Pearson correlation coefficient. Pearson product moment correlation coefficient. Product moment isn't really that important, but you should remember Pearson core, the Pearson correlation. What is the Pearson correlation? Let's identify it. In terms of the covariance. So what have we done to the covariance to get Pearson R? We divided it by the product of standard deviations. So what could we call it?
Standardized covariance.
You got it. Standardized covariance. Yep, standardized covariance. Pearson R is the standardized covariance. I'll put it right here. We're done with this. So Pearson R is the standardized covariance. Is the standardized covariance. Now let's ask the question, why is R better than just the covariance? Well, for one, what have we done? We've placed limits on it, right? We've placed bounds on it. The max